Thank you for inviting me to come. I am passionate about the research that I've been able to do over the years, and I'm passionate in sharing all of that as well. And as part of that, I should explain a bit about the GeoPrisms program. It's one of the challenges in our sciences is to study processes that span the land and the sea. And so the concept of the GeoPrisms program was to, for what many of you may not realize, sorry, let me just explain. At NSF and in many agencies, there's land-based work, and then as soon as you require a research vessel, you become ocean sciences. And it's like there's a wall or a divide and a communication barrier, even in communities that don't interact too well. So GeoPrisms brings those folks together and has recognized how much we can learn from active observation of our process. So you can take that information and apply it to ancient plate tectonics examples, or vice versa, share aspects of the ancient that are exposed in the rock and place that back in a context with the active deformation. So, you know, we bring people together coming in with different disciplines, and we have workshops and meetings to bring people who are studying volcanology through petrology, through geochemistry, through geophysics, or, you know, any of these processes. We bring the different groups together, sedimentologists, and they talk to each other and try to look at new multidisciplinary science. So there's like cohort building for graduate students and communication across disciplines. So I'm part of that program. And what I'm illustrating is how we can work together and work on multidisciplinary science to solve what look to be, you know, really big systems-related problems, but through this communication and re-education. You know, it takes us when you're working with somebody from a different field, you almost have to learn a lot of new vocabulary, do some additional reading, and pick up that field as well. So anyway, what I also wanted to say is that I've had the privilege over the past, well, as an undergraduate, I got involved in research. And I went to East Africa on an expedition to survey for drilling sites for climate change studies in the East African lakes back when people thought that they were maybe 100,000 years old and maybe had 100 meters of sediments inside them, and I'm going to show you it's completely different. And our whole vision of the way continental rifting takes place has changed drastically since that time. But I'm also going to try and point out to you too how natural curiosity and investigation can take you to places and can also, you know, have you translate your scientific skills into topics of societal relevance, or communicate that and try and make some changes as well. So there's a whole range of ways we can take our sciences skills. So this is an example. You may have seen this. You probably think this is a road. It's actually a camel track. It's like this wide in the dust in the desert. And these are active fault systems in the Afar Depression. And this is actually an explosive crater of a fissure along, or it's called a rent along the edge, and it's exposing lavas in the Afar Depression. But, you know, really active processes and this pairing between faulting and magmatism that's really important. So I'm going to talk about that. Now, here you are in West Virginia. Most of your classes are probably using examples from North America, where we have a lot of information. Your field trips are going to be to these places. And you're saying, she's going to show us examples from Africa? Why? And the reason is that the East African Rift is active now. And there are aspects of rifting that can only be studied in that area. So if we want to actually directly compare the rates of opening and the rates of magma production, or to actually quantify the fault kinematics, and then do the modeling, numerical modeling to simulate process, we need this active information. So I'm going to take you to that place, but just here, and not too far to the east of here, the basement underneath the Appalachians is an ancient rift basin. And there's oil exploration in sedimentary basins worldwide. And so our active studies, in a way, are like studies on a time slice in a hydrocarbon exploration or a geothermal exploration strategy project. Okay, so if that helps you. So it's the active part of the process. But I'll bring you back at the very end of the talk to the mid-continent rift system that goes from under parts of the Mississippi, up through Wisconsin and down into the Great Lake, beneath the Great Lakes system, and show how what we're learning in East Africa informs what we know about how North America was created a billion years ago, more than a billion years ago. Okay, this is a pretty messy diagram. And for now, just ignore this B, section B. I'm not going to say anything about that, but we'll talk about this and this. And I want to try to point out how we can look at a problem and say there are many processes occurring. How can you understand the dependencies between those different processes? So let's just say, and this is what's a bit, well, in this system, we'd start off with lithosphere that might look like this. So here's our crust, there's our mantle, and it would be simple, flat. As we pull on it and stretch it, we will start to thin different layers. They may thin at varying rates. So there's less crustal thinning and more mantle lithospheric thinning in that diagram as I drew it. And that may be the case in many situations. So that's, that's a variable that we have to consider. As this thins, the asthenosphere rises upward passively in response. And, oh, thank you. Okay. Oops, this one, there. Okay, so it can rise upward. As it rises upward, just like when you uncork or take the lid off your Coke bottle, you'll have carbon dioxide that was in solution that'll come out because the pressure is released. The same kind of pressure then releases volatiles, gases, move upward. Primarily water and carbon dioxide are the primary components, and that can also induce some small amount of melting depending on the temperature of this material and how high it rises. So as you get to less than, say, 80, 90 kilometers, you're generating some basaltic melt as you're pulling the material upward. Underneath thick lithosphere, you may generate very little, and it'll come back to the petrology part in a second. But we're pulling, and there are passive responses because we're preserving, we're changing the density structure of the plate. So you see here, the base of the crust is upwarped. So in that section then, the density structure there is completely different than the density structure in this column over here. So what happens when you change the densities across a sheet? What'll happen? Things go up and down. Isostasy, remember? So we can do isostatic balances and look at the topography. The topography is hugely informative about what and where these density changes are occurring. And also gravity anomalies tell us many of these things. If we have upwelling, then we're also going to have a counterflow across this region. So we'll have inducing some kind of flow in the system. So we need to include and think about fluid dynamics. Maybe a member of the team needs to be good at this and add those components. What happens when we generate magma? Well, it's buoyant. It's less dense than the surrounding material, so it rises upward. As it rises upward, then it rises to a level where it's roughly the same density as the surrounding material. And the basaltic, hot molten basaltic lavas may trickle upward and get to the base of the crust, where they're about the same density as lower crustal material, and then may stall. And that's the start of a magma chamber because it's no longer buoyant and can't rise anymore, but it's still too hot and not frozen yet. So these are the things that are happening in a rift system as time is going on. Up here on the top is just a picture. We all know that mid-ocean ridges, we have passive upwelling, generate some melt, and there are thin dikes or sheet-like paper. They have the dimensions of a piece of paper. So very, very thin, but long and tall. And they provide a conduit to bring lavas up to the surface, and then we have the pillow lavas that form the oceanic crust. And so underneath then, we have a column of these dikes in the system. And a dike also creates topography. So when we inject one of these dikes, we uplift the shoulders adjacent to them. So they contribute to the topography in the rift system, and then the lava flows do, the volcanoes themselves. And so we're constantly changing the system as we keep stretching. And we consider the force balances going on. We also get clues, really important clues, from the time scale of the process, because earthquakes may happen. We may be, so you build up stress over a long period of time, and then the rocks fail, and we have slip. So the slip happens really rapidly, but the stress buildup for the next earthquake may take 1,000 years. The time period between volcanic eruptions or intrusions that never make it to the surface may be a shorter time period. And then we also have water loading and unloading just with seasons in any one area. So we're changing the stresses in the system on a seasonal scale. And so these are all the time factors. When we're involved in active deformation, we need to be sure that this surface uplift and subsidence, or the changes in vertical elevation, aren't related to the water cycle or the hydrological cycle as well. So we think about all of these, but volcanoes respond to these changing stresses. So I don't know whether you knew this, but submarine volcanoes are most likely to erupt at eruptions are triggered by the tidal cycle, and sometimes even by the lunar cycles as well. So when we have larger stresses, the tidal stresses, then we're more likely to have a volcanic eruption. So take something that's nearly critical, just like those games that you play where you pull out the blocks, and they're near critical, and it only takes a breath of air and you push them over. So it's that kind of part of the system that we want to get to. We want to understand eventually how to predict earthquakes, and we're getting much, much closer to understanding when and where a volcanic eruption would take place. So those are some of the societal relevance aspects that I'll just touch on very quickly at the end. So here's the way I'm going to present information. So let's go back to this diagram for a second. If you can see, there are what we might call bottom-up processes. So we're moving material up in the system, we're changing densities, and those are being driven from underneath. So mantle convection, or this thinning process, and the gas release, those are the bottom-up. The top-down processes are the creation of topography that change then the gravitational potential energy. Gravitational potential energy is mass times gravity times the height. So something that's higher has more gravitational potential energy. It's more likely to fall down than something that's low, right? So high elevations are being pushed down by gravity, and they are more likely to extend. And it's a crazy thing to say, but that's why mountains, like the Himalayan, the Tibetan plateau, why it can't just keep building higher and higher and higher. Because it can't against gravity, and there's gravity trying to keep it flatter, and obviously through time they'll go lower. So we have top-down processes and bottom-up processes, and then we have mass transfer between the different layers. So I'll try and help you understand the importance, how we separate out the different importances, and how this teamwork then works, how we work together to solve these important problems. And I'll show you some discoveries that we've made as well. So one of the things that is important are, where did our atmosphere come from? Volcano degassing. So over time, volcanoes that degas created the atmosphere, and they contribute to our composition of the atmosphere as well. Here's a volcanic eruption at a volcano. I'll show you in a few minutes. The structure, we had a project to study the structure underneath this volcano. It's actually, it's called the Donyolengai volcano, and it erupts lavas that are unusual, and that they erupt at 400 to 450 degrees centigrade instead of 1,200 degrees centigrade. And so you can get a bit closer. They're also very fluid. So their viscosity is about 1/8 that of a basaltic lava. These are the fault systems just behind this volcano. And of course, working in East Africa, it's great because you can use zebras and giraffes and water buffalo for scale in your diagrams whenever you're presenting. I don't always get to work in game parks, but I have had the opportunity recently. Now, what you can't see is the silent thing that's going on here, but there's CO2 coming up these fault systems back behind here. I'll show you that this CO2 it becomes a really important clue and an important contribution to the global cycle. So here's a really simple block diagram of how the carbon flux works, the different contributions and sinks, sources and sinks to the global carbon cycle. And we're really concerned about carbon, both in taking CO2 out of the atmosphere, putting it in repositories, but we want to understand the system completely before we start to sequester CO2, and also to understand better the Earth system as well, and these feedbacks. So here's like, just taking like a cross section, flattened it all out into a map. This would be the outer core, the inner core, and we might have plumes or topography or low density zones at the core mantle boundary, like mountain belt. There's mountains down here at the core mantle boundary. Some subduction zones, the plates go all the way through the mantle transition zone here at 410 and 670 down into the lower mantle. Sometimes the plates stall up in here, but some of them make it through, and then we flux material back upward through mantle plumes, ocean islands, and back at mid-ocean ridges as well. So here's a mid-ocean ridge. Down here then, these are the numbers, or these are the sources in terms of grams of 10 to the 13th grams of carbon per year. I don't know how big that is. That's probably like a football stadium full of carbon, but mid-ocean ridges contribute a little bit. Volcanic arc systems contribute quite a lot. Continents are reservoirs of carbon because we have plants, trees, plants, all those kinds of things. And then we bring sediments and others back down into the subduction zone to maintain this whole cycle. And through here, we trap some into the prisms. But one of the things you'll notice on here is there's no continental rift. Whoops. So until at the time of this paper, they didn't think it was significant and weren't concerned about it, and said, well, you can just consider it back here in back arcs. It's a really small amount, so this number back here for the arcs. So part of one of our studies then is to look at that as well. The global water budget, likewise, is important in considering. This is from a recent paper by Parai and Mukhopadhyay. And they, just in saying these are the sources and sinks then of the different components of the water cycle. And so volcanoes are really important. The mid-ocean ridges are a contribution, but nowhere in here is anything from the continents. Continental rift zones were just neglected from this, yet they cover a large portion of Earth's surface. So it's just that there'd been this gap in our knowledge. And I'll try and point out how quantifying the carbon cycle has helped us understand large parts of this whole system as well. So the bottom-up parts of the process. So, okay. So what I'll do, I'll try and put in throughout, kind of like intermediate, I'll put some little mini summaries and then move on, but I'll try and highlight again what we're learning from the bottom up in both that and then the top down processes. So we know worldwide that the scales and architecture of continental rift zones vary from place to place. So if you've been out in the Basin and Range province or some of the extensional systems in Greece or Turkey or someplace, even in China, there are areas where we have extension from places that were high plateaus in a collisional belt. So even as in Italy, the Apennines are a collisional belt, but they're coming apart now in extension. And there was extension and collision going, or not collision, subduction going on roughly at the same time. Built up a higher plateau and it collapses under gravitational potential energy. In those cases though, we have a difference in the rheology. And I started to draw something up here. I'll put a sketch up and just explain a little bit more as well. But the rheology of the plate or the time-dependent behavior is going to have a large role. And so places where we had mountain belt systems, we thrust material up, bring material from lower levels, transfer heat, and create really hot crust. And that's really different from a rift that develops in cratonic lithosphere. So here's another important thing. Comparing and contrasting and finding end members gives us a way to start to identify the important factors or the feedbacks within these systems. So we can't figure out all the physics straight away, but we start to try and eliminate some possibilities and start to focus on what we're doing. Then the other thing to remember too is that rocks are much weaker in extension than they are in compression. So a fallback from this is that, fortunately, because rocks are weak in extension, we don't build to magnitude 8 or 9 earthquakes in extensional provinces because rocks fail first. They're weaker in extension. Then the opposite side is we get less information from the earthquakes. Because for these maps over here of global earthquakes, there's nothing smaller than a magnitude 4.5 or 5 on those maps, and because that's as good. We can only globally detect earthquakes with the broad, wide array with those magnitudes. So we get smaller magnitude earthquakes, meaning we need to go local and put instruments out to get a better idea of what's happening. Okay. Also, when you're pulling on something and stretching it open, you're creating open fissures or fractures. So these are dilatational fractures, and that is then a better conduit for magma to get to the surface. So you expect to see more magma, or smaller amounts of it coming up along lots of fractures than you do in a compressional belt system, where it's harder to get, there are fewer fractures to get the material up. Okay, so it's a different style of volcanism than you get in magma processes in extensional environments. Okay, so let's go back to this rheology part, because I just said it was important, so what am I talking about? Okay, so I'll try here, and if you don't quite get this, I can go to the board and explain a little bit more. So here's the differential stress applied to a particular material. So obviously it's under some stress, it's under some pressure at any depth within the earth. And so this would be any additional stress applied to it. It might be a plate tectonic stress, or adding a weight on top of it as well, or some change. So if we apply a stress and we assume a friction law, Byerlee's law is one, we can assume then some kind of frictional strength to a material. So it's resisting fracturing or failure. Okay, so how do we know? We pull on something, how do we take material properties and say, well, will this cause an earthquake? Well, we take them in the lab and we do these kinds of tests and come up with the curves like this, where here's depth within the earth, here's a quartzite-rich rock. If we assume we have a 40-kilometer thick section of mostly quartzite, which is way too simple for the crust, but we'll just take this example. Here's where the failure would occur at how much stress would be required. So to cause failure at this depth. This number here, 0.4, this would be the pore fluid. So if we have some fluids in the rock, just a little bit, okay, they're pushing outward and decreasing the strength. So that's why the shape of this curve looks like this line here. So anything more than this, we should get failure. Anything less than that, the rock can withstand it without failure. This intersection underneath is what we call the ductile deformation curve. And that means that we have a rapid decrease in the strength of the material because it starts to flow. So it reaches failure, and perfectly elastic material would fail, and then stress would build back up again. This is when you reach that failure, and then the rock starts to deform more like in a ductile way, or more like silly putty or something like that. And so this is showing that we have a rapid decrease in strength, and we don't expect to have earthquakes at all down here. So we might have some in this zone, and these numbers, these are actual observational data, pressure temperature conditions, and strength measurements from a recent paper by Baer and Platt, and showing these fit very well with theoretical curves. So this is a theoretical curve taken from a laboratory. So if you do an experiment with big problem with rock physics, you'd have to have multiple graduate students over about 100 years to do an experiment to study at the slow rates of plate tectonic processes. So we speed everything up in the laboratory and then extrapolate to slower rates. So that's a bit of a guess, but this is showing that the rock data is showing a pretty good match, the geological rock data. Anyway, my point here is that as we this would be for quartz, there's a different shape curve for different types of rocks and whether or not they're hydrated. So hotter and colder rocks, a hotter rock is going to, or a higher geothermal gradient, means the rock is going to have less strength. And so this curve might start up here. And so these kinds of comparisons are important, and understanding where the earthquakes are occurring is telling us about the strength of the materials as well. Okay, so let's go to the bottom-up processes. And one of the reasons that I'm working in East Africa is that, well, here, this is as if we were looking at a map of Earth's core mantle boundary. And the red are hot zones, or so slightly lower velocity and lower density zones. So lower velocity is associated with higher temperature. Always the same composition in the mantle, so it must be a temperature-related anomaly. And there's this massive hot zone. No, remember, it's not that big. The radius of the Earth is decreasing. You know, we get down to the core mantle boundary and the radius is much smaller. So this is stretched kind of way too big. If you map it back down, it's a smaller area. But this is roughly under where it would lie, and there are many hotter zones coming up from the upper mantle. So this is the African superswell area. There's another big area in the South Pacific. This is harder to study because you'd have to have instruments on the seafloor and do all these experiments on the ocean, where every day at sea might cost $30,000 just to move the ship back and forth, let alone do any science. So we've been studying this area for a while, and we're trying to understand these hot zones beneath, rising up. So we know we have this hot area moving up from the core mantle boundary, and then we move up, and I'm just taking one piece of that Africa area. So now we're in the Horn of Africa. This is Ethiopia, where we've done a lot of work in Ethiopia, collaborating with the Addis Ababa University scientists and the Geological Survey. We've also been working in Yemen, which is now quite a mess, but some great research that's been done here in Yemen too. This corner of Yemen used to fit somewhere down in through here, and it's stretched away in the last 30 million years to open the Red Sea. Here's the Gulf of Aden coming down here. So all these blue dots, okay, these triangles are different where we had seismometers out over the past decade, and blue are the dots of where the earthquakes globally, so an earthquake in Japan, the seismic waves coming from Japan would come up and penetrate the base, and intersect with the mantle transition zones. The mantle transition zone is that section of the mantle where we have phase changes. And nobody really understands whether we trap fluids, whether they can move freely across. And new studies, and so here, this is a cross-section right through this area here. And what you're looking at then, so this is 100 kilometers, 2, 3, 4, 5. This is the 410 discontinuity. This is the 670 discontinuity. And they're like seismic reflections. And these are from the bottom up, though. So you take an earthquake somewhere in the East Pacific Rise, or in the Mid-Atlantic, or in Japan, or somewhere, Tonga, and they come, and the waves come up, and they give a reflection from those boundaries. So there's a reflection here at the 670, and then this is the 410. But in between, there's a change in phase, indicating there must be something that there's a fluid phase in here, and it's most likely melt. So there's melt being generated at this transition zone, coming upward, and this negative zone is interpreted as aqueous fluids coming upward as well. So what we think is happening throughout the superplume province, as it gets shallower and shallower, water and magma are starting to be generated even at these great depths, and they're moving upward. So the plumes are transferring a lot of water. And that's something that's testable, and I'll show you that this is what the petrologists have been telling us for a long time. Okay, so the other thing we can take seismic waves from distant earthquakes, and instead of using, say, the reflections, the P waves or the S waves, we can use the surface waves. And the surface wave gives us a really good depth extent, but not really good lateral spatial coverage. And the surface waves show us how thick the lithosphere is. So the lithosphere is the crust plus the mantle part of the lithosphere. And we can see that this Horn of Africa area is quite thin lithosphere. And then we have thicker cratons, really thick craton underneath Congo, Zimbabwe craton, and the South African craton, the Capval craton down through here. This is a bit surprising here, but there may be another remnant of a thick craton that's unusually thick. So these are more than the blues are more than 180 kilometers thick. So we have huge variations in lithospheric thickness. And that's really important. So if we have something rising upward, it's going to interact with these different depth levels, right? And so that topography, so we have mountains at the base of the plate. And just like an iceberg with isostasy, you see only a tiny bit of it, and most of it's under the surface. And this is what we're seeing, that the mantle lithosphere is varying from, say, 80 kilometers to 160 kilometers, 180 kilometers over short distances. Those are huge numbers. So most of the topography is at the base of the plate, not at the top of the plate. And that's a big component of that. Now, the other thing that we can see, if I map out, if I say, take all the earthquakes in a catalog and sum up all the energy, make the magnitude scales all the same, and sum them up at each little half-degree cell, I can then say that's equivalent to, say, a magnitude 4 earthquake, or a magnitude 5, or a magnitude 7 or 8. Everything that's deeper blue than about this is a 6. So all of these areas in here are experiencing large amount plate boundary type deformation, energy release, strain, deformation across those areas. Some of these are quarry blasts in South Africa, so this is unusual, ignore that, but the rest of it is showing us how Africa is coming apart. This is most of the continent of Africa has earthquakes. And there are earthquakes that are expected now. Folks used to say, oh, these were just inaccurately located. No, there are active faults. We now have good topography. We can see the structures extending through here into the Congo craton. There are earthquakes in the Tanzanian craton in through here. There are earthquakes in the Zimbabwe craton. But then there's some places where we see something that looks almost like a rigid plate with hardly any earthquakes. So we see earthquakes around the edges of this block in through here, and then hardly any inside. So, the continental plates and the plate boundary zones are really big and broad, and we have distributed deformation, and some of it comes back and matches these edges that we're seeing here. So what the lithosphere was like at the time of any tectonic processes is really important. It's going to be important in terms of magmatism too. So one of the things that, this is a paper that literally was just out. Right now, we don't have a lot of GPS information that's showing us how fast the plates are moving. So in this case, this is a paper by Stamps and Soria, and they kept this part of Africa rigid and allowed no deformation, which, if you go back to the earthquakes, that's not actually a legitimate thing. So they put an edge here and said all the deformation's happening over here, and ignored, they said that was rigid. That's not necessarily true, but we didn't have GPS stations, so they just ignored it. And all of the blue are where there's actually data. Now there are more continuous GPS sites in West Virginia than there are on this entire map of most of the African continent. So that we don't know an awful lot, but we know that the plate's moving and there are variations spatially. So there are things rotating by small amounts as well. So we have rotations about vertical axes in some of these little microplates, and this looks like one of these. This is the one I was showing you before with earthquakes around them, but there's actually a plate boundary offshore here. There are volcanoes through in here. There's a lot going on in a broadly deforming zone. Okay, so I'll just summarize in here then that we know from theoretical models that the forces available to stretch apart a plate are smaller than the strength of the plate. We know that the plates are thick, yet we can see that it is deforming. So in the thin zones, we understand. Up here where it's thinner, that makes sense. But over in here, it defies what we had thought about the strength of the plate. And the difference, the reason is those fluids coming upward. So when you add fluids from the bottom to different rock compositions, remember Bowen's reaction series, what do you do if you take an olivine or a dunite or a Harzburgite rock and add some fluids to it? It changes composition, right? So we're going to talk about, and metasomatism becomes a really important process. Okay, so I've just said this really, but what I'm now going to point out is cratonic roots and also slabs divert mantle flow. So plates are moving, and these mountains and valleys underneath the plates are changing the way the mantle flow is occurring, and there are little upward directed currents. If you have an upward directed flow, you can extract a little bit of melt. The higher the upward directed velocity, the more melt you can create, and so we get a lot of volcanoes in the African continent. So let me move on. Keep moving. Okay, so the cratonic edge, this is just a normal plate with a big cratonic edge, and these arrows here are showing the mantle flow. There are ways we can reverse the direction of flow. If we hydrate the bottom, then the flow direction will be upward, but these edges of cratons, they thin and erode laterally this way. You don't burn a hole from the bottom up. You remove material by enhancing the mantle flow. So these are numerical simulations of flow along an edge. And in this case, the material is actually coming downward, and we have a counterflow bringing material upward from a hydrated base of the lithosphere. So we're transferring material in the system and changing the lithospheric thickness, stripping away material. Okay, I'm going to skip this. And now just move on quickly to show you some new results from an area in southern, in this area here where we have thick cratons and then we have a big red blob. So what do you think is the red, this pinkish blob right there where the lithosphere is much thinner? Any guess? Magma and volcanoes, you're right. Yeah, it's a Rungwe volcanic province. It's an isolated volcanic province that's persisted for at least 17 million years. A really small volume of melt. So nothing's happening. It's just kind of dribbling up, and occasionally we'll have a massive explosive eruption, a Plinian eruption, and then it goes quiet. But small volumes of magma, these are effective. So these are surface waves, and say 40 seconds is the mantle beneath the crust. These are periods of the different waves. It's harder to translate them to depth until you have independent information that's just coming out of this project, but what's important for you to just see is that even from our local studies, we had about 100 seismometers out here, including some beneath Lake Malawi, OBSs beneath the lake, ocean bottom seismometers, but they were lake bottom seismometers, and at anything in the lower crust and in the upper mantle, we just see this red blob, and then everything's cold adjacent to it. So that's generating melt and coming upward. Well, why do we have a spot? We have thick lithosphere here, and then we have something in between. Well, one possibility is these ancient variations. Here's a craton, and in between is a thin zone. There's mantle flow in this direction, and when it comes to this bend, there's what's called a stagnation point. So you move the flow, so you flow, as it bends this way, you get an upward directed flow pattern in through this area that's suggesting that we have, that might explain the magmatic province. So how do we know how the mantle's flowing? What kind of observations can we use? Well, we can use mantle anisotropy, and I'll come back to this slide for a second and just look at this diagram over here, because I don't want to go into too much detail, but if seismic wave is propagating in this direction, as it goes into a material that is, let's just take this part of it. So there's a wave that's propagating vertically. As it goes through the layered media, the wave that's propagating in this direction is moving a little bit faster than the wave that's propagating in this direction because it's going through crystals that are anisotropic. So olivine, for example, is more than 20% faster in one direction than another. and the olivine crystals align in the direction of mantle flow, so we get an indication. The fast direction is the mantle flow direction. So we use this seismic splitting, and what we do is try and find out the time differential to correct, to bring that wave exactly to match this one and this one. So we can do these corrections on the computer with different distant earthquakes, and we can map the mantle anisotropy patterns. And these are the things that we get. I'm not going to say anything about the Virunga province here, but I'll just show you. Here's the normal African plate motion. Direction is northeast, northeast, and we get into the rift, and it shifts, and it goes northwest. And it goes parallel to the rift up through the thin zone, and it's vertical beneath the volcanic province. So that's suggesting then that we have motion in this direction and diverted flow in the thin zone. So just the lithospheric thickness variations are driving the mantle flow, and perhaps explaining why the deformation is where it is. So now the thing what I want to wrap up with, what we see at the surface, where we have earthquakes, where we have volcanoes, that's where features make it to the surface, and that's where we localize the deformation. And that's the whole process of rifting. So you may have deformation across a broad zone, but to actually rupture the plate, you have to localize all the stresses to a narrow zone, or all the strain to a narrow zone, sorry, to allow the plate then to rupture. And so that strain localization process is the progressive deformation process we really want to understand, and it's hard. So one of the things I'm going to look at then is this: what happens when you add magma? Because I talked about the fluids and putting water into the lower part of the plate and reducing its strength, how CO2 can change that as well, and I'll just give you a flavor of some of the new studies that we've been undertaking. So I'm going to show you some information from the East African Rift again. I showed you some the bottom-up processes here. I'm going to go into this area over here. Now, Africa, it's complex. The ages of the parts of the rift are quite different, but all of these little red triangles are active, are Holocene volcanoes. So they've been active over a short time period. There are many, many more older volcanoes throughout Africa. So there are volcanoes all over. There are volcanoes here. There are volcanoes on the seafloor. Whoops, sorry, just down here. So magmatism is an important process in Africa. You don't hear about the eruptions, but they're quite important. Rifting's been going on for 20 million years or so in most of the rift, and in some places even longer. So now I'm going to take you to this place here at the Kenya-Tanzania border. This is Tanzania down here, Old Onyalengai volcanoes there, Ngorongoro crater. And these are some of the experimental data that we've had out. These are existing data from the area, and I'm just trying to help you out here. But it's a fantastic place for a safari if you want to go, and you can sometimes climb this volcano if it's not in a period of eruption. So what did we find underneath the volcano, and how does it help us understand the strain localization? Well, pieces of information we need. We want to know how thick the crust is, how the stretching is distributed across the area. Ideally, we want to know what the mantle looks like underneath, and that part of the process is nearly finished. But I'll just say that there's very localized thinning in the mantle lithosphere. But I'm going to focus on the crust now. And what we know is that we have big fault systems along the basin, and that we have massive amounts of carbon dioxide coming up the fault systems. Not up the volcanoes, but CO2. CO2? What? Is that from organic material and the breakdown of organic material? Nope. It's magmatic CO2. The carbon has a mantle signature. And so what we are finding is that there's lavas or magma coming up, not lavas, magmas coming up here to the base of the crust and stalling, but they're large volume, and the gas is then coming up and using and escaping along the fault systems in the basin. So there's lots of CO2 here and CO2 here. The earthquakes are occurring in the lower crust. Wait, but there should be no strength in the lower crust. Well, in this case, it's still pretty cold. So if you heat something from below, it takes a very long time for the upper part of the crust to actually get hotter. So the heat transfer in this case is coming from the intrusion of the lavas, and this crust above it is still pretty cold. So we have earthquakes occurring in the lower crust, and then magma is rising up into some of these areas. Down here on the bottom, this is a P-wave velocity anomaly map. And this is roughly adjacent to the edge here. We have a sharp edge where the CO2 is coming up. And these reddish areas then are low velocity zones. This is a lower crustal magma chamber, and this is a sill complex with sedimentary sequences throughout this area and here. And I'll put that all together into a story. So this is work that a large group of people, there were 6 institutions involved in this project, many graduate students, and a large number of undergraduates. So some of the work that I'm showing you here is from a paper where there were 7 undergraduate research students who worked with me over a period of 3 years, several of whom went out to the field and collected the data and analyzed them. So I'm really proud of the work that they did. So one experiment mapped out the base of the crust using receiver functions or bottom-up reflections. This is the tomography. We looked at earthquake focal mechanisms and mapped out then where these magma bodies would be. These are earthquake focal mechanisms here. And you'll look at that. If for some of you who've looked at earthquakes, you'll say, wait a minute, that has too much black. How did you color it in? Did you do that wrong? What happens if you have an earthquake, okay, that's assuming the faults are slipping in some sense like this or like this. Just rotate the plane. But if as the faults are slipping, they're also opening up, there's a bit like an explosion component or dilatation along that, and that causes an everywhere upward directed force as well. So the combination of the two of them lead to these funny focal mechanisms. So in this area, there was a volcanic eruption in 2008 here, but it was provoked by a dike intrusion over here, and then immediately afterward, there was this volcanic eruption. And the earthquakes that we're measuring in this area then are showing this active magma process. That active magma process is allowing up to more than 5 kilometers of new igneous material, and that new igneous material is degassing and the CO2 is coming to the atmosphere. So how significant is it? Well, here you go. This is just a cross-section. This is just showing cross-section. These are all the sampling places, simplified for the Rift Graben. But these are the large volumes. These are larger than are even measured in Italy near volcanoes in thick carbonate sequences. So it's quite a lot. And what they show is that the faults penetrate to the lower crust where the magma is being intruded because the fault systems are a permeable pathway up to the surface. And the other thing that we can work with from the seismic imaging is estimate the magma volumes. And the magma volumes, or the rates of magma addition, are the same as what we see on volcanic arc systems in subduction zones. So rifting processes are an efficient way to create new continental crust and may have been the important crustal accretion processes in the very early stages of Earth formation. And this is just a histogram to give you an idea. This is how much, in terms of a global flux in megatons per year, these are the world's biggest polluters of CO2, and that's Africa, near Congo. Etna's in Italy, Makajima's in Japan, and those faults in the basin are as much as the most gaseous volcanoes in the world. And if you now add the East African Rift, it's a really important contribution to the global carbon cycle. So what does that mean now? Let's go back again and kind of close this all up for the bottom-up processes. So this is my colleague Toby Fisher, who worked with us on this part of the project, followed up then with those gas studies and the gas volumes, and explained then the evolving chemistry as adding water to the base of the plate in these areas here, and we can see the changing lava chemistry and the eruptive chemistry. So at the edges of the rift, we get carbonatites, then we get these melanites that are derived from hydrated but deep, high pressure, and then we get basalts in the middle of the rift. And that's what I just showed you from the section, from the rift section. And this is then the kind of way that we burn away the base of the plate and allow the mantle, now take a cratonic lithosphere that's too strong to stretch apart. Well, it's not too strong if I add water and then allow these to either generate melt or be stripped away in mantle convection. So plates and cratonic roots can be destroyed by these hydration processes through the mantle plume fluid upwelling from the core mantle boundary up towards the surface. And I just put this on here again to say that those pictures then are like this right here. So you remove the material and strip it off at the edge and break into the thick craton. And that then explains how we can have faulting strain within the middle of a craton. So I'm just going to stop with this part. I had a second example of deep earthquakes in the crust, but I'm just going to leave to say that in 3 different areas now in East Africa, we're seeing this at very large amounts of mantle lithospheric thinning, small amounts of crustal stretching, CO2 degassing, dike intrusion, migrating earthquake swarms, and volcanoes at the surface. And volcanoes that are unusual compositions derived from a thick lithosphere, a thick but hydrated lithosphere. So just to summarize then, in these time-space patterns, the strain localization within the crust and the mantle part of the lithosphere is strongly influenced by volatiles and magma. So one of the things that we're now adding to our arsenal of tools is to go out and make soil gas measurements in rift zones and figure out where, as a tool to say, is there magma deep down that's not reached the surface yet? Because we can sniff it through these soil gas measurements, and we can start to better understand the process. But we're realizing that hydration and magma generation is much more prevalent than we had thought. That the magma pulsing then is kind of like in the earthquake cycle. Dikes intrude at much smaller stresses than are required to overcome friction along the fault, because the buoyancy force of the magma is helping push it upward. So they're kind of earthquake silent. So we've missed them in the record. So we've underestimated the strain rates. We also want to say that rift zones are an area where we can create new crust. So that's important in terms of global Earth processing over time. And adding the gas, putting the gas in along the fault systems increases the pore pressures. And that can induce small earthquakes, but it also weakens the rocks, and it also then enhances these positive feedbacks that weaken the plate and promote then strain localization. So that's how we can localize the strain to one spot and allow plates to then eventually rupture to create new ocean basin systems. So, a combination of I'm going to go back to this diagram because I really love this picture then is kind of a final way to summarize. But continental rifts were neglected in terms of global fluxes of CO2 and water. They're an important component, and they're also areas of new crustal growth. And there are scars of rifts everywhere, like the one I was saying just near here, the Rome Trough, from the Iapetus stage of rifting in North America. There are filled rifts all over. And let me just take you to one more. Sorry, I'll get you to here. Not far away from us is the mid-continent rift of North America that comes way down. Okay, so we're over here, but you can see all these purple are 10-kilometer thick or more lava sequences in basins going all through the area, back down into Michigan. So we're over here, but this occurred over 1 billion years ago and left this massive volcanic section with mostly new crust that was created in this rift. So that's another example of one of these just here in North America. So thank you.